Well, good afternoon, everyone. Yes, like Val indicated, I'm going to try to give you some overview of some observations that have been made on the 21 to 23 Fagradalsfjall fires and 23 to 25 Sundhnukur fires in the Reykjanes Peninsula in Iceland. And the emphasis will though be on melt compositions and their implication for the magmatic system that actually produced these eruptions. You never walk alone. There's a lot of people who contribute to this, and a few other names are there. Now, most of you are probably familiar with that Iceland is located in the North Atlantic, and also it's linked to the Reykjanes Ridge system, and basically the Reykjanes Peninsula is an on-land continuation of the Reykjanes Ridge, where you can see the sort of the Reykjanes Rift come ashore on the western side of the peninsula, and then it's a transtensional system that extends across the peninsula, links the Reykjanes Ridge with the western volcanic zone in Iceland. Oh, sorry, yes. Forgot here. So we have here, start with this, you see the location of the Fagradalsfjall fire fissure or volcanic lineament. And please note that this actually took place in a fairly poorly fractured block between two rifts, whereas the Sundhnukur volcanic lineament is actually inside of the Reykjanes Rift, and is actually took place on an existing volcanic lineament, the Sundhnukur volcanic lineament, and also reactivated the Grindavík Graben. So it's a pre-existing structure that got reactivated. Now, the Reykjanes Peninsula through time has been characterized by magmatism of initially by pickrite eruptions, small lava shields, and that was superseded by eruptions of olivine tholiites in form of fairly large lava shields in the early part of the Holocene. And in the latter part of the Holocene, we still have olivine tholiites, but they're mostly from volcanic fissures. In the last 3,000 to 4,000 years, the activity has been typified by, like I said earlier, by emissions from volcanic lineaments or volcanic fissures. And they have occurred in distinctive eruption periods, which have each lasted for about 300 to 400 years. And they are actually separated by repose periods of 600 to 1,000 years, where we have no volcanic eruptions in the peninsula. And in these repose periods, what you're doing, you're basically just stretching the block that is actually represented by the Reykjanes volcanic belt. And in about 800 years, you can actually stretch it up to about 16 meters. And then when you reached kind of a critical state, you get actually a failure, you initiate extension of episodes and eruptions, which actually last then for 300 years. So that's what we are facing at the moment. And the people who live in Reykjanes Peninsula are going to be faced with this for the next few hundred years. And this is just an overview of the eruptions so far, as presented by Julius Dr. et al. In 2025. The biggest eruption still is the first eruption at Geldingadalur in 2021. It's about 0.1 cubic kilometers, and it's about double the volume of the next one, which is the Sundhnukur 6 eruption. Sundhnukur fires generate a fairly larger flow fields, have more aerial extent, slightly more volume, but compared to the Fagradalsfjall fires eruptions in 21 to 23. Also note that the magnesium content of the erupted melt, these are glass compositions, have changed from the Fagradalsfjall fires from being 7.5 to 8.3 weight percent down to 6 to 6.8 weight percent in the case of Sundhnukur. And all of these are significantly smaller than the eruptions at Holuhraun in 2014 to 2015, which is order of magnitude bigger. Now, this diagram kind of seems scary to start with, but it's actually kind of a summary of the whole activity. On the x-axis, you have time. Here on the primary y-axis, we have the normalized sort of number of earthquakes and also seismic moment. On the secondary y-axis here over here, we have the both the erupted volume as well as the volume accumulated in a shallow magma chamber prior to eruption, shown here in green. The bars at the bottom show the duration of each event in days. The upper panel is basically the horizontal displacement on 4 stations, 2 on either side of these volcanic lineaments. And if we look at this a little bit closer, we can see that the Fagradalsfjall fires, which is shown here in orange, they began with a fairly powerful or intense seismic activity or episode with a really high seismic momentum, a lot of earthquakes, but a fairly moderate extension. And this is followed by 3 other events, one in December 21 and then 22 and 23, where you've had a moderate extension and fairly moderate sort of seismic moment or seismic activity. And by late 2023, the activity shifted to Sundhnukur volcanic lineament, and that started with a major extensional event on the Grindavík Graben, and this has been quite well known, but a very moderate seismic activity. This is actually consistent with the fact that here we are actually reactivating pre-existing systems, whereas in the 2021 case, we are actually opening a fresh pathway in a fairly unbroken block. Also, associated with the Sundhnukur activity, it started fairly moderately in terms of magma, both accumulation and output, and this increased significantly in the later periods of this activity. It's clearly showing that we start here with extension, and then the magmatic activity picks up, suggesting quite strongly in my mind that actually the extension, the opening of the fractures and the activity that led to the eruption eventually is the tectonic part of that is actually what happens first, then the magmatic part comes in. And in this context, it's important to actually remember that not all, 6 out of 8 of the eruptions on Sundhnukur volcanic lineament started on a segment which is 500 meters long in the same place. And the position of that part is actually in such that the only way you can get magma there is vertically through a well-established conduit. So ideas about lateral flow, I think, are overrated in terms of explaining what happened in Sundhnukur. Now let's look at some of the magmas. Start with whole rock compositions. This is actually the erupted magmas in Reykjanes Peninsula during the Holocene, ranging from picrites to olivine tholiites, and they're all fairly depleted. They have very low potassium titanium values. And if we look at the whole rock values for the Fagradalsfjall fires and also for the Sundhnukur fires, we see that the lowest potassium titanium values are at the upper boundary of the Reykjanes trend, but they extend to way much higher values, indicating that we have a new fresh batch of magma coming in that has not erupted previously on the Reykjanes Peninsula. These define actually quite nice mixing trends. If we look at the melt compositions, this is actually from tephra deposits, we can see that in general they show that the melt composition shows the same trend as the whole rock compositions, except they're significantly lower in terms of magnesium or shifted to lower magnesium contents. And the difference between the whole rock and the melt or the glasses is about between 2 and 3 weight% magnesium, indicating that there's a significant amount of more mafic macrocrystal as carried by the magma towards the surface. So there's an extra component in there. If we look at the glacier salvages, we see that they basically define the liquid line of descent, which is actually produced by degassing-induced crystallization in those melts as they flow away from the vent. Now, if we compare all of this data with melt inclusion data that is published by Thordarson et al. 2022 and also by Matthews et al. In 2024, if we start with the Thordarson data, which is all from Geldingadal eruption in 2021, we see very easily that all of the melt inclusions have higher magnesium number than the erupted melt in the Geldingadal eruption in 2021. Most of them also have lower potassium titanium value. Basically what that is telling us is that these melt inclusions have no relationship with the erupted melt and their host crystals neither. So they're actually xenocrysts. They're actually added cargo to the erupted melt. And they provide no information about the melt or the magma that was erupted. Now, the story is a little bit better for the Sundhnukur ones, where the melt inclusions kind of follow the glass compositions. So if we look at data from Thordarson et al. In terms of geobarometry, we've already established that the melt inclusion that they use to actually infer the very deep source for the magma, it doesn't apply, so we can take that away. If you look at the OPAM results, you can see that data from glacier salvages, which should give you basically surface pressures, is giving 5 kilometers depth. So I would say that raises questions about the validity of the OPAM. Sorry, I went the wrong way. And we're left with a pyroxene geobarometry, which gives a depth of about 11 to 12 kilometers, which is actually very similar to what has been established by seismic tomography studies, where people see actually a significant anomaly about 9 to 12 kilometers depth, which we think is actually the source, magma source for that produced the Fagradalsfjall products. And also, if you look at the Sundhnukur geobarometry, we can see that the OPAM gives actually quite reasonable estimates for the surface samples and indicating about 4 to 5 kilometers depth for the magma storage, which would then kind of fit nicely with the fact that the inflation source beneath Svartsengi, which is estimated to be at 4 kilometers, that was basically the source magma storage for the Sundhnukur fires. And this fits also with the difference in magnesium contents. Now let's run through the glass composition. This is the first melt that erupted in Geldingadal in 2021. It's a depleted magma, and basically what we see here is the composition of the glacier salvages, which define the liquid line of descent or the fractionation trend. This was followed in days 13 to 38 by magma that's slightly higher in the potassium titanium values. And then for the remainder of that eruption, from day 31 to day 180, we have magma that is actually fairly enriched and high potassium titanium values. And most of the lava salvages over here correspond nicely with having been produced by degassing-induced fractionation, but a lot of them are actually down here, suggesting that they've actually gone through some mixing in addition to the fractionation, and that mixing must have taken place in the lava flow itself. And 2022 and 2023 events of the Fagradalsfjall fires, they show kind of a similar values in terms of potassium titanium trends, and but slightly lower magnesium content, so they're slightly more fractional, probably by fractional crystallization. And oops, I'm going the wrong way again. Also, what happened in 2022 is that the Meradali lava was loaded onto the lava formed in the 2021 eruption, which still had a liquid core, and it's actually squeezed out the liquid core, and the glaciers from that actually fit nicely with what we see for the glacier salvages of the material erupted during the 21 eruption. So it's clearly from the 21 lava flow. Now to Sundhnukur. Initially, most of the magma or the melt that was erupted actually shows fairly elevated potassium titanium values, but one comparable to actually being fractionated from the mixed magma of the Fagradalsfjall fires. There's also this component down here which actually is depleted, and as you see in the following slides, this component increases as a component in the erupted material as time went on. And it's compatible to the depleted magma that was erupted in Fagradalsfjall or the Geldingadal eruption in 21. So we'll just run quickly through this. And you can see that all of these things sort of fit with fractionation from the mixed magma here or the depleted source. So to finish this off, just kind of a synthesis, in 2018, we see the first indication of actually magma starting to accumulate underneath Fagradalsfjall into the Fagradalsfjall magma storage, which was an existing storage. It's not a new one. And by 2020, that has kind of reached some maturity. And also at that time, people detected inflation of Svartsengi, and that's been interpreted as CO2 influx by all of the Flóans and co-workers. In 2021, we get the first eruption from the Fagradalsfjall storage, and starting with the depleted, then the mixed, and then the enriched component. And our interpretation in late 2023, we had shut down Fagradalsfjall, and we opened up the Sundhnukur system, and it's basically reactivation of a pre-existing plumbing system, and the more enriched magma up here accumulated in the shallow magma chamber, fractionated, and then erupted. And this was then followed by eruption of more depleted material. As this storage here just got heated up, you remobilized actually existing magmas in that storage. And that's sort of been taken over in terms of magma output in the most recent eruption at Sundhnukur. And with that, I'll say thank you.
We are running a little short of time. Is there a very quick question for Thor? Please.
Thank you for the talk. Do you see reactivation of the other systems along the peninsula?
Yeah, well, we see indication of reactivation by seismic activity, and there's a fair bit of seismic activity at depths that where we suspect that their magma storage might be located. So yes, we do see that, and that's the Reykjanes, further out on the Reykjanes, the tip of the Reykjanes Peninsula, also further inland in Krýsuvík and even over to Brennistisfjall. So most likely we will see eruption from those systems in the near future.